three integrals here, which we're going to solve by doing something to the top and the bottom of the fraction, multiplying the numerator and denominator. In the first case, by 1 minus sine x. So I'm going to call this one part 1, part 2, and part 3. I know they haven't labeled it like that. I just think it helps to divide them into these sections. Part 1, come back to the integral in a minute. Let's sort out this 1 over 1 plus sine x. I'm going to times it by 1 minus sine x over 1 minus sine x. And that is going to be equal to 1 minus sine x. And I get a difference of 2 squares, 1 minus sine squared x. And now it becomes clear why we just did this, because the denominator simply becomes cos squared. We've managed to get it from being two terms to just a single term. So I can then write it as sec squared x, 1 over cos squared, minus sine x over cos x times 1 over cos x, which is sec squared x minus tan x sec x. And actually we know how to integrate both of these. So I1 is going to equal the integral pi over 0 to pi over 4 of sec squared x minus tan x sec x. Tan differentiates to sec squared, so sec squared integrates to tan. And then sec x actually differentiates to tan x sec x. So I'm just using my knowledge of those. We can write it straight down like this. Now to put some exact values in, tan of pi over 4 is equal to 1. Cos of pi over 4, I haven't learnt my reciprocal exact trig values. I just work out what cos is, and then I'll do 1 over it. So here I get 1 over root 2, or root 2 over 2, but it's going to be easier to write it like that. So tan of pi over 4 is going to be 1, minus sec of pi over 4 is going to be root 2. And I'm going to be minusing tan of 0 is 0, cos of 0 is 1, so I'm going to be minusing 1 here, which gives me my answer of 2 minus root 2. Okay, that is our solution for the first integral. Just very quickly, one alternative for dealing with sine x over cos squared x, and actually I use this idea later on, is instead of writing it as sec x tan x, to write it as sine x times cos x all to the minus 2. When you get something in this form, we can see that we know the derivative of cos is related to sine, so we kind of have it in the form f of x and f dash x, roughly speaking. Okay, there needs to be some minuses and need to deal with that minus 2, but it's in that form. So we can use reverse chain rule. We can simply increase the power of cos x by 1. And that's our like trial function. What happens when we differentiate this? I would do d by dx of cos x to the minus 1. I bring the minus 1 down and lower the power, and times by the derivative of the inside, so minus sine x. And actually we get exactly the same thing. So it's just going to be 1 over cos x plus c in this case, which is identical to sec x that I found before. But it's just that this, you might prefer this as an alternative. Look at the next one. So this is what I called part 2. And I'll define this just in case I need to reference it later on as I2. So first up, 1 over 1 plus sec x. Well, we saw how well it worked in the first part, so it kind of makes sense to try the same again. If you didn't get an identity that worked, you could obviously very quickly return to the original. Sometimes you have to try things out. But this is going to work, in fact. I'm going to get 1 minus sec x over 1 minus sec squared x. Okay, trig identities. I never remember them, I just always deride them. So sine squared plus cos squared is 1. Of course, I remember that one. Right, if we want sec squared, divide through by cos. So I'm going to get tan squared plus 1 is sec squared, which means 1 minus sec squared is going to be minus tan squared. So 1, actually I can just swap it around and make it sec x minus 1 over tan squared x. And then that will become sec x cot squared x minus cot squared x. I'm going to need to play around this slightly. It's not quite in the right form because the derivative of cot is related to cosec. So let me write it as, let me just focus on this one actually and write it as sec x times, now cot is cos over sine, so it's going to be cos squared x over sine squared x. Actually, the sec and one of the cots is going to cancel. So we're left with cos over sine, cot x, and then a 1 over sine, so cosec. Right, that's looking better. Because I know how to differentiate that. It's a little bit like that sec x tan x one. The derivative of cosec is minus cosec cot x. So we can deal with that. Cot squared, right, there's a particular way to deal with integrating tan squared and cot squared, and it's actually to return to the identities. So I've not written down this identity yet, but we could take that starting one and this time divide through by sine squared. So 1 plus cot squared is going to be cosec squared. So I can replace this by cosec squared minus 1, but then I'm minusing it. So actually, let me just replace the whole thing. Minus cot squared is going to be 1 minus cosec squared x. So that means that I2 is going to be the integral from pi over 4 to pi over 3 of cot x cosec x. Then I'm going to get plus 1, like, because I've already dealt with that negative, I'm basically adding minus cot squared x, but then I said that cot squared x was 1 minus cosec squared x. It's going to be plus 1 minus cosec squared x. So here I get minus cosec x, because the derivative of that, the negative cancels out. Then I get a plus x, and over here, actually, it's going to be cot x that differentiates to minus cosec squared x. So this is even going to be a plus. A lot of integration by inspection going on here. You can, honestly, as I'm doing this, I don't even know which formula in the formula book, so they, of course, might help you out too if you've got that in front of you. Okay, a few more trig values to think about. So sine of pi over 3, same as sine 60, that is going to be root 3 over 2. And sine pi over 4 is 1 over root 2. Then tan pi over 3 is root 3. And tan of pi over 4 is 1. So minus 1 over root 3 over 2 is going to be minus 2 over root 3. Then plus pi over 3 plus 1 over root 3. That's the first bit. And I'm minusing sine of pi over 4 was 1 over root 2, so it's going to become minus root 2 plus pi over 4 and then plus 1. That's going to give me 1 over root 3, sorry, pi over 3 minus 1 over root 3 plus root 2 minus pi over 4 minus 1. A third minus a quarter is 4 over 12 minus 3 over 12. 1 over 12. So I'm going to get pi over 12. Then I'll write plus root 2 minus 1 over root 3 minus 1. Can't really simplify that much. I could rationalize the denominator of the 1 over root 3, but this is absolutely fine. So that is our second integral. Before I move on, I'm just going to show you one alternative and reference another one. So it's quite nice actually. We could take the integral and add 1 and minus 1 to the top, split it into two parts, and basically get an integral that's very similar to part A over here, which you can then do in the same kind of way. So remember we had 1 plus sine x, but 1 plus cos x on the bottom will work in a very similar way. An alternative second method is actually to use half angle formulae. I'm not going to go through that one. Have a look at the official solutions. Quite interesting, but it feels like more complicated. So this final integral here, part 3. Okay, well, why not take this 1 over 1 plus sine x and do the same thing again, times by 1 minus sine x all squared. I know without the square there, I'm going to get 1 minus sine squared. So I'll deal with the top in a minute. Because when I put a pair of these brackets together, I'll get 1 minus sine squared. So it'll be 1 minus sine squared x all squared. And then I'm going to expand the top. So I'm going to get sine squared x minus 2 sine x plus 1 all over, okay, here comes cos to the power of 4x. All right, that makes things a little bit more complicated than the previous questions. Let's keep going with this. I'm going to write each term, like separate them into three fractions. Sine squared x over cos to the 4x. I'll come back to that in a minute. Then minus 2 sine x over cos to the 4x plus 1 over cos to the 4x. Now that one looks the trickiest. How to deal with that? We'll worry about that in a minute. So sine squared over cos squared is tan squared. This is going to become tan squared x sec squared x. And actually, that is really good. You can do this using inspection because when you differentiate, because the derivative of tan is sec squared. So I've got a function and something to do with its derivative there. I'm going to be using the reverse chain rule, but that will work out. I don't need to do anything else with it. Over here, I've got 2 sine x, and then it'll be cos x all to the minus 4. This is also very, very good because I've got a function and then its derivative here. So I can bring them together using inspection again. That just leaves us this 1 over cos to the 4x. I had to think about it for a while. I thought, okay, surely we can do this unless I've made a mistake. This is going to be achievable. Doesn't seem to be a quicker way to do this question. Can't really mess around too much with the cos to the 4. That actually only leaves us messing around doing something with that 1. Let's write it as sine squared plus cos squared. It's not like this is a standard integral, but you're sort of expected to play around with it, realize that you can do something with it. And this is going to work out really nicely. So I'm going to get another sine squared x over cos to the 4x. Yeah, I've already got one from here. And then I'm going to get a sec squared x. So actually, I can just write the full integral down now. I3 is going to be the integral from 0 to pi over 3 of 2 tan squared x sec squared x. See, because I've got one here and I'm adding another one on. Then it'd be minus 2 sine x cos x to the minus 4. That's okay. Plus sec squared x. So we're going to use a trial function here of tan to the 3x. Because when I differentiate that back, I'm going to get 3 tan squared x, dealing with the outside, times the derivative of the inside, sec squared x. So all I need to do is divide by 3. I've got the 2 from before there. There we go. For the next one, I can do a trial function of cos x all to the minus 3 because I've increased the power by 1. So then I'll get minus 3 cos x all to the minus 4. And I'll times by the derivative of cos x, so minus sine x. These two cancel. So again, I'm very, very close. I just need to divide through by 3. If I put a third there, then it will all work out. I just then need to obviously times through by 2. So 2/3 cos x to the minus 3. And then sec squared, that's the simplest one, is going to be tan x. Okay, I've written some of these exact tricky values down, but let's just do them again. Tan of pi over 3 is root 3. Tan of 0 is 0. Cos of pi over 3, not written this one down, as a half. And cos of 0 is 1. So I just write those two down. 2/3 times root 3 cubed minus 2/3 times a half to the minus 3 plus root 3. Then minus 0 minus 2/3 times 1, so that I can ignore that, plus 0. Root 3 cubed is 3 root 3, so I'm going to get 2 root 3 here. A half to the minus 3 is 2 to the 3, so it's 8, so I'm going to get minus 16 over 3. And I'm plussing root 3, adding to root 3. And we're basically there, so I'm going to get 3 root 3 minus 14 over 3. That works out really nicely. Brilliant. Only thing I would add to this solution was if you think you wouldn't have thought of the one what I did here with cos to the 4x, 1 over cos to the 4x, which actually works out so nicely, then here's an alternative. You could integrate by parts. I wouldn't have thought to do that. Sec squared times sec squared, and then integrate one, differentiate the other. So I guess, yeah, that works out as well. Bit more complicated, I think. But there we go. Really nice question.